Pick any 4-digit number. It does not matter which one, as long as its digits are not all the same. Take 3,524. Now do something almost mechanical to it. Rearrange its digits into the largest number you can, then into the smallest number you can, and subtract the smaller from the larger. The biggest arrangement is 5,432. The smallest is 2,345. Subtract, and you get 3,087. Now just do the same thing again to the answer. Sort 3087's digits high and low. Subtract, and you land on 8,352. Do it a third time, and you get 6,174. And here is the thing worth staying for. If you keep going from 6,174, you get 6,174 again. It stops moving. That by itself would be a mild curiosity. What makes it strange is that we did not choose 3,524 for any special reason. Almost every 4-digit number you could have picked ends at this exact same value, and it gets there fast. This whole video is about why one ordinary-looking number swallows nearly all the others. Before trusting a pattern, pin down the rule exactly, because the whole effect depends on doing it the same way every time. The routine takes any whole number of 4 digits. Write those 4 digits in descending order to get the largest value they can form, and in ascending order to get the smallest. If a leading digit turns out to be 0, you keep it, so the number stays 4 digits wide. Subtract the smaller from the larger. That single subtraction is one step, and the answer becomes the input to the next step. There is exactly one number you are not allowed to start from, and it is any number whose digits are all identical, 1111, or 2222, or 9999. For those, the largest and smallest arrangements are the same number, so the subtraction gives 0, and 0 just stays 0 forever. Every other 4-digit number, and there are 9,990 of them, has at least 2 different digits, and those are the ones we care about. So the rule is short: sort down, sort up, subtract, repeat. No arithmetic beyond a single subtraction. Nothing chosen along the way. It is completely determined by the number you start with. And that is what makes the ending surprising, because a rule this rigid has no obvious reason to funnel everything toward one place. Watch what that rigid rule does to numbers that have nothing in common. Start from 1,000, a number that is mostly zeros. Sort and subtract, and because of the leading zeros, the first answer is just 999, carried as a 4-digit value. Keep going, and after 5 steps you arrive at 6,174. Now start from 9,998, almost the largest 4-digit number there is. Completely different digits, completely different path. It also collapses to 999 on the first step, and then walks the same last few numbers down to 6,174. Try 4,321, whose digits are just 1, 2, 3, 4, in order. 3 steps, and again 6,174. Every road leads to the same town. That destination has a name. It is called Kaprekar's constant, after the person who found it. And the remarkable claim is not that some numbers reach it, but that all 9,990 valid ones do. Not most. All of them. The first thing to understand is why 6,174 is the place everything stops, and not some other number. Apply the routine to 6,174 itself. Its digits are 1, 4, 6, and 7. The largest arrangement is 7,641. The smallest is 1,467. Subtract, and you get 6,174, exactly what you started with. That is what makes it a fixed point. It maps to itself, so once you land on it, you never leave. And among all 4-digit numbers, it is the only one besides 0 that does this. 0 is the trivial one, the collapse the repeated digit numbers fall into. 6,174 is the only genuine one, the single value the routine cannot push off of. A fixed point on its own does not have to attract anything. Plenty of rules have a resting value that nothing else ever reaches. What is special here is that this one pulls. Think of it as the drain of a basin. No matter where you pour the water in, it runs downhill to the same low point. 6,174 is that low point, and the entire 4-digit landscape tilts toward it. There is a second surprise hiding inside the word fast. It is not just that every number arrives, it is that none of them takes long. For any valid starting number, the routine reaches 6,174 in at most 7 steps. Not 7 on average, 7 as a hard ceiling. There is no 4-digit number anywhere that needs an eighth. If you sort all 9,990 valid numbers by how many steps they need, the counts are lopsided. Some reach it in 1 step. The largest single group takes 3 steps, and a big block, 2,184 of them, needs the full 7 before they settle. Here is one of those slow ones, worked all the way through. Start from 2005 and count 5,175, then 5,994, then 5,355, then 1,998, then 8,082, then 8,532, and finally, on the 7th subtraction, 6,174. 7 steps, and then it is trapped. We set the repeated digit numbers aside at the start. They are worth a proper look, because they are the only numbers that escape 6,174, and understanding why shows how narrow that escape is. Take 1,111. All 4 digits are the same, so the largest arrangement and the smallest arrangement are identical, both 1,111. Subtract 1 from the other and you get 0, and 0, sorted and subtracted, stays 0. So these numbers do not reach 6,174, they fall straight to nothing. But count how many numbers this actually removes. There is exactly 1 repeated digit number for each digit from 1 to 9, plus the all zeros case. 10 numbers in total out of 10,000. That is the complete list of exceptions. Every remaining 4-digit number, all 9,990 of them, flows to 6,174. So the exceptions are not a crack in the pattern, they are the smallest possible footnote to it. 10 numbers sit out because they have no digits to disagree, and literally everything else is captured. A rule that misses only 10 targets out of 10,000 is about as close to universal as a rule over the 4-digit numbers can get. The natural next question is whether 4 digits are special, or whether any length of number has its own constant. The answer is the sharpest part of the whole story. Try the same routine on 3-digit numbers. Sort down, sort up, subtract, repeat. It works the same way, and it too has a single destination, 495. Every 3-digit number with at least 2 different digits reaches 495 in at most 6 steps, and 495 maps to itself just as 6,174 does. So far it looks like a general phenomenon. But now try 2 digits. There is no constant at all. Instead, the numbers fall into a loop that cycles through 9, 81, 63, 27, 45, and back to 9, going around forever without ever settling. 5 digits behave no better. There is no single number that everything reaches. Instead, there are several separate cycles, and where you end up depends on where you began. So the clean, single drain behavior is not a general law of the routine. It happens for 3 digits and for 4 digits, and then it breaks. 6,174 and 495 are special to their exact lengths, and nobody has a simple reason why those 2 lengths cooperate and the others do not. The person who noticed all of this was an Indian schoolteacher named Dattatreya Kaprekar, who described the 4-digit result in 1949. He worked mostly alone on recreational number problems, without a university post, and for years his findings were dismissed as beneath serious attention. The routine that now carries his name is elementary enough for a child to run by hand, and yet it took a particular kind of attention to sit with an ordinary calculation long enough to notice that everything drained to one place. And here is the honest ending. We know 6,174 is the constant, and we know the 7-step ceiling because someone checked. Every one of the 9,990 valid 4-digit numbers has been run through the routine, and all of them land on 6,174 within 7 steps. That is a complete proof, but it is a proof by exhaustion, not by insight. There is no tidy formula that says why this number, why 7 steps, why these particular lengths. So 6,174 is a settled fact with no deep reason attached, the mathematical equivalent of a locked door, whose key we have, but whose mechanism we have never seen. You can verify it completely and still not understand it. That gap between knowing that something is true and knowing why is where a lot of good mathematics starts.